So for our sign off video, we're going to talk about volume one last time, right? So volume, and so it continues. We're going to talk about volumes of pyramids, and we're going to talk about volumes of cones. So first, we're going to start with cones. So if we're going to talk about cones, we're going to have to start with where they sort of derive from. Let's talk about the cylinder. We said that the volume of a cylinder is going to start with the area of the base. So volume is going to be equal to pi r squared, right? The area of the base times that sort of vertical space that area occupies as we go down to the other parallel base, right? So that distance, right, I'm going to say D for distance, is referred to as H in the formula as height. But it's not always a height. Sometimes the formula is laid down on its side. Well, now, what about a cone? Let's take a look at the first scenario. So what we have here is a cone. And this cone has the same height as the cylinder, has the same size base as the cylinder. And what I've done is I've filled this cone up with water and I dumped it in, and we're at this height. That's cone number one, trying to fill the cylinder. Cone number two. Well, what do we notice? A little bit more water, right? Again, same height, same base size, a little more water. Cone number two. On cone number three, you'll notice that plus or minus a little bit of spillage, we have now completely filled the cylinder. So it took 3 cones to make one cylinder when they share the same size base, right? So the base is being the same, the height's being the same. So if the volume of a cylinder was originally pi r squared, the area of the top or the base, times the height, if it takes 3 cones to make one cylinder, then how do we go in reverse? We divide by 3 or multiply by 1/3. And there's the volume of a cone formula. And that's where it comes from. So let's get down to the other specifics. Now we're going to be talking about pyramids and we're going to be talking about cones. So what's the difference? Well, obviously a pyramid has a base that is some sort of polygon. Now it seems to me that this is a square pyramid versus a cone has a base that's a circle. So really the base is the difference, right? The base is the main difference. What's similar? What's similar is that they're both 1/3 the space that they take up of the actual prism that they occupy. So a cone, it's not really a prism, but the cylinder, that's 1/3 of that original space. And if this was a rectangular prism, it would be more like, excuse my inability ad hoc to draw a good 3-dimensional prism, but you get the point. So what's similar is that they both occupy 1/3 of the space, or 1/3 of the volume. The mathematics behind this isn't very difficult. It's just a matter of being careful. I guess you know where I'm recording this now. So again, we're going to roll with the same process. First, we're going to want to identify, right? Identify the figure. So this is a rectangular prism. And if it's a rectangular prism and we're looking for volume, volume is going to be equal to 1/3 big B times H, where big B is the area of the base. And the base in this particular case is a rectangle. So volume is equal to 1/3 area of the base, I'm going to leave inside here, times the height. Well, it looks like the height comes off the base at 90 degrees, so that's going to be 5. And it's a rectangle, so 21 by 9 is the area of the base. Now, how you want to process this is up to you. We can say 21 times 9 is 189. And so we have 1/3 times 189 times 5. Now you can either divide 3 into 189 and multiply it times 5, or multiply it times 5 and then divide by 3. It doesn't really matter, but at the end of the day, you should get 315 cubic yards. So that's the amount of space inside that pyramid. Riveting. Moving right along, what do we have next? We have a triangular pyramid. And so the base of this pyramid is a triangle. And the height of the triangle and the base are always connected by a right angle, which makes this the height of the triangle. But I don't know that. I do know it's a right triangle, so I do know that 14 squared plus x squared equals the hypotenuse squared. And the hypotenuse is always across the street from the right angle. And as I process this, I'm going to say that x squared is equal to 22.1 squared minus 14 squared. And after I take care of everything and do all of the correct mathematical procedures, I'm going to get that x is equal to 17.1. And actually not approximately, but exactly 17.1. Okay, so now big B in my 1/3 base times height formula, right? That big B is going to be the area of the base. And the area of the base is a triangle. So that's 1/2 times base times height of this triangle at the bottom, the base, which is 1/2 times 14 times 17.1. Okay, that's your big B. That's going to yield us an answer of approximately 119.7. So I come back over to my volume. That's 1/3 times area of the base, which is 119.7, times the height of the actual pyramid, which hits the base of the pyramid at 90 degrees. So that's times 19. And again, using order of operations properly, we should yield an answer of 758.1 cubic meters. And that is our volume. I'm sorry, I keep writing area over here. That's a major faux pas. I will correct that. My apologies. Now we're heading back into the cone where this whole conversation started. And again, this is a cone. I'm identifying the figure. Volume is equal to 1/3 pi r squared, right? Which is essentially the area of the base, the circle, times the height of the cone. And again, think of this as the distance from the bottom of the cone to the top of the cone, but the cone's laying sideways here. So volume is going to equal 1/3 pi times, well, diameter is equal to 5 inches. So radius is going to be equal to 2.5 inches, half the diameter. So that's 2.5 times the height, which is 8 inches. And now just take your time. I mean, I guess the safest bet would be to take all of these and multiply, and then at the end, divide that all by 3. And then come at this with a final answer in cubic inches. The last couple are the thinkers. And again, you can't run from this. You know, if you want to deal with reality-based mathematics, there are word problems or application problems. If you don't put a little bit of effort into trying to understand some of the mathematics of life, you're doomed to struggle. And I don't want you to struggle. So let's see. Caitlin must build a sandcastle. We're going to build a sandcastle. And it's in the form of a square pyramid. So that's our base. And it says shown to the left, but I've moved this to the right. I've changed it a little bit. On your notes, it's on the left. She bought 3 bags of sand, each containing 1,200 cubic inches of sand. Will she have enough sand to build the castle? Well, I guess we're talking about volume, right? So the question is about volume. Does she have enough? Volume of a square pyramid is going to be 1/3 times the base times the height. And the base in this scenario is a square. So area is equal to side squared. So we just come off to the side and work a little math magic. 1/3 times the area of the square is 25 times 25, or 25 squared. That's the area of the big B base, times the height of the pyramid, it's the base at right angle, is 18. And these are all in inches, so that's good. So let's see. So we'll take this one at a time. 1/3 times 25 squared. 25 times 25 is 625 times 18. And then we'll say 1/3. 625 times 18 is 11,250. And then you're going to divide that by 3, and you get 3750. Now this is volume, and this is cubic inches because it's three-dimensional, as mentioned in the previous video. Now, she bought 3 bags. 3 bags. Each bag contains 1,200 cubic inches. So 1 bag equals 1,200. So if you take 12 times 3, you get 36. That means that 3 bags is equal to 3,600 cubic inches of sand. She needs 3,750, so what's the answer to the question? Will she have enough? I think the answer to the question is no. She is short, and I know plenty about that, by 150 cubic inches of sand. But really, in reality, she's 1 bag short. You can't go to the store and just buy a portion of a bag. So that's our scenario. I think at the end of the day, our final answer is this answer, but you have to have all that work to show and support it. This next question talks about having 2 congruent hollow cones. So here's a hollow cone. So this space in the cone and this space in the cone is hollowed out. If the cylinder's height is 20 inches, okay, so this is 20 inches, and the diameter is 14 inches, so all the way across is 14, find the volume of the solid. So I think the solid is the gray portion. So this is the solid, and this is the solid. So we need to remove the 2 cones. So this is going to be a 2-step process. First, find the volume of the cylinder. Step 1. Step 2, subtract the volume of the 2 cones. All right, so I've shrunk down that space to give us a little bit of working area. So volume of the cylinder is going to be pi r squared times the height. And, right, so this is the cylinder. All right, so I know that it's going to be pi times the radius is 7 because the diameter is equal to 14, so the radius is equal to 7. And again, this is in inches. So pi times 7 squared times the height, okay? And the only thing we're squaring is the 7, so that's pi times 49 times 20. And pi times 49 times 20 is going to yield us 3,078.76 cubic inches. So that's the volume of the cylinder. Now we need one of the cones, and then we're just going to multiply it by 2 because it said that the cones were congruent, 2 congruent cones. Now these intersecting pieces are intersecting halfway. So it would be safe to make the assumption that the height of the cone is 10 inches. So volume of the cone is going to go like the following. 1/3 times pi r squared times the height, which is 1/3 times pi. The radius is still 7 squared times 10. That's one of the cones. And again, take care to just multiply the 7 times itself. Don't square both 7 and 10. Don't square 70. We're just squaring the 7. And the volume of one cone is worth 513.13 cubic inches. This is one cone. So we're going to take our cylinder, which is 3,078.76 or 3,078 and change, minus, and then I got to take two of these 513s. So when I take the 513, I multiply it by 2, I'm going to subtract 1026.25. And again, this is 2 cones worth of volume. And so the volume of the remaining portion, our solid, is 2052.51 cubic inches. So that is the volume of the solid. On number 11, again, looks scary, really not. All we have to do is approach this as 2 cones. The big cone and then the small cone. And if they want the volume of the shaded area, then I guess I'm just going to do big minus the small one on the top will give me the shaded area. And all you need to do is use a little bit of addition and subtraction to deal with the volume of the cones. So you can go ahead and finish on your own. For this particular piece, you're going to have to go back to your last set of notes. The volume on the bottom here is a triangular prism, okay? This is not a pyramid. So you're gonna have to deal with the triangular prism. And then on the top, you have a triangular pyramid. So again, we want the total volume. So if you want the total, I guess we're gonna add. Again, sorry about the bell. We're gonna add those 2 volumes. And this one you're also going to finish up on your own. So you could do this. Remember, we're just about there. Hang in there.